Yes, now in this video we continue our properties of Poisson distribution. The next interest is the recurrence formula for central moments. This recurrence formula for central moments will offer the higher order moments of normal Poisson distribution. We already found the first central moment first row moment mu1 dash as lambda and second central moment mu2 as lambda. So mu1 is 0, that is the first central moment, mu1 is 0. First row moment mu1 dash is lambda. When we list the central moments, mu1 is 0, mu2 is lambda. So next our interest is to get the higher order central moments like mu3, mu4, etc. So for that we have a recurrence formula to recur the moments, central moments of Poisson distribution. So we are now coming to the derivation of this recurrence formula. We have its equation mu r plus 1 equal to lambda d mu r by d lambda plus r mu r minus 1. This reference formula can be used to determine the successive moments. That is, if you know the first moment mu1, the first central moment mu1, we can determine mu2, and using mu2 we can determine mu3, etc. So it will act like a chain rule, and that is the advantage of this recurrence formula. So we don't come to the derivation or the central moments separately or this recurrence formula for central moments. So for example, you take r equals 1 and r equal to 1 we get mu r plus 1 as mu 2. So mu 2 is equal to, that is the left side, right side will be lambda into d mu 1 by lambda, that is in the place of r we put 1, that is d mu 1 by d lambda plus r into mu 0. This r is now actually we can take it as 1 because we already assume r equals 1. So it is 1 into mu 0. That is, when we put r equals 1, the left side is mu r plus 1 mu 2 and the right side is lambda into d mu 1 by d lambda plus 1 into mu 0. We know already that mu 0 everywhere 1 and mu 1 everywhere 0. That is, 0th order central moment is 1 and the first order central moment is 0. Mu 1 is 0. Since mu1 is 0, its derivative with respect to lambda is also 0. So when we substitute these things here, it is lambda into d mu1 by d lambda 0 plus, that is 0 plus 1 into 1. Mu 0 is 1, so 1 into 1. So it is actually lambda into 0 plus 1, that is lambda. So mu 2 equal to lambda. The same result we obtain using the direct derivation, that is what we found in mean and variance of Poisson distribution, that is mu 2 equal to lambda. So the recurrence formula also generates the central moment, second central moment very successfully, that is mu 2 equals lambda. Next we find mu 3. For that we put r equals 3 in this equation, that is 2 plus 1. Mu 2 plus 1 is mu 3. So mu 3 is equal to lambda into d mu 2 by d lambda plus 2 into mu 2 minus 1. We can see here mu 3 equals lambda into d mu 2 by d lambda plus 2 into mu 2 minus 1, that is d 2 mu 1. But mu 2 is lambda. In the former step we found mu 2 as lambda. So d mu 2 by d lambda is 1. We already found mu 1 is 0. Generally mu 1 0 everywhere. So it is mu 3 equals lambda into 1 plus 2 into 0, that is 1 plus 0 again inside the bracket, that is mu 3 equal to lambda. So it's a very peculiar property of Poisson distribution, that is the first row moment, that is mean, then variance and also third central moment. So all these things are equal to lambda, that is once again mu 1 dash, that is the mean, and second central moment, that is mu 2, and third central moment mu 3, all are equal to lambda. Now when we come to the fourth central moment r equals 3, there is slight difference, it's not lambda. So first of all we find mu 4 by putting r equals 3 in this recurrence formula. So we get lambda into d mu 3 by d lambda plus 3 mu 2. That's by putting r equal to 3 in the above equation. We know that mu 3 equals lambda. So its derivative with respect to lambda is 1. So it is mu 4 equals lambda into 1 plus 3 lambda. That is, this d mu 3 by d lambda is 1 plus 3 into lambda, that is 1 plus 3 lambda. In short, the fourth central moment is mu 4, that is equal to 1 plus lambda into 1 plus 3 lambda. So these are the four central moments of Poisson distribution. I repeat once again, mu1 is 0. That is a general result everywhere. For any distribution, mu1 is 0. The second central moment of Poisson distribution is lambda. Third central moment is lambda. And fourth central moment is mu4, that is lambda into 1 plus 3 lambda. So now we can make use of all these four central moments for finding the skewness and kurtosis of Poisson distribution. We have the measure of skewness given by this beta 1 equals mu 3 square by mu 2 cube, mu 3 square by mu 2 cube. So when we substitute here, it is lambda square by lambda cube. That is, in the place of mu 3 we have lambda and mu 2 also lambda. So lambda square by lambda cube, which is 1 by lambda. So the coefficient of skewness is given by gamma 1, which is root beta 1, that is equal to 1 by root lambda. So we know that this value of gamma 1, that is coefficient of skewness, is 1 by root lambda. It's always positive. It cannot be negative at any moment because lambda is by definition taken as positive lambda. And even if gamma 1 we consider only positive root of lambda, so nothing makes it negative. So gamma 1 is positive. So it means that gamma 1 greater than 0 always, as the frequency curve of Poisson distribution is positively skewed. And this is situation unlike we found in binomial distribution. In binomial distribution, we found gamma 1 as q minus p. We can refer to that in that screen of uh, binomial distribution. Gamma 1 is q minus p by root npq. I shall open that screen of binomial distribution measure of skewness. You can see that it is q minus p by root npq. So therefore, it is here q greater than p, q less than p, q equals p. There are three different instances that makes gamma 1 positive, then negative and equal to 0. So the skewness of binomial distribution depends on the values of q and p. Here nothing to say like that. Here always greater than 0, so it is always positively skewed. We also note that this quantity 1 by root lambda becomes smaller and smaller when lambda becomes larger and larger. So that is an indication of this frequency curve becomes symmetric. That is, the frequency curve becomes symmetric when lambda tends to infinity, or when lambda tends to infinity, gamma 1 tends to 0 and the frequency curve becomes symmetric. Next we come to the measure of kurtosis. The measure of kurtosis is beta 2. It is given by mu 4 by mu 2 square, that is 3 lambda square plus lambda, that is the equation of mu 4 divided by mu 2 square, that is lambda square. So when we divide this lambda square with 3 lambda square plus lambda, that is separate, we get 3 lambda square by lambda, that is 3 lambda square by lambda, which is simply 3 only, plus lambda by lambda square, and which is 1 by lambda. So we have this 3 plus 1 by lambda. This is equal to 3 plus 1 by lambda. So which means that gamma 2 equals beta 2 minus 3, and that's equal to 1 by lambda. And here also it's an indication of leptokurtic, because when depending on the value of gamma 2 we have the interpretation about the shape of the frequency curve, that is gamma 2 greater than 0, the frequency curve will be leptokurtic, and if gamma 2 less than 0, the frequency curve will be platykurtic, and gamma 2 equal to 0, the frequency curve will be mesocurtic. So here we know that the value is always greater than 0. 1 by lambda cannot be negative at any point, so it is greater than 0, the frequency curve is always leptokurtic. But we also note that when lambda becomes larger and larger, for greater values of lambda, this gamma 2 will be 0, therefore lambda tends to infinity, gamma 2 tends to 0, and that's a situation where the frequency curve attains mesocurtic shape. So when gamma 2 tends to no, when lambda tends to infinity, gamma 2 tends to 0, and the frequency curve becomes mesocurtic. We can interpret the same result in terms of the frequency curve graphically. I have drawn various frequency curve of Poisson distribution for different choices of lambda. So the first is the situation where lambda is equal to 0.5. So 0.5, I have found out the values of the probabilities of the values of So this variable following Poisson distribution with lambda equal to 0.5, then P0 is 0.6065. That is by putting the value, shall I write the equation of the Poisson here? It is e raised to minus e raised to minus 0.5, then 0.5 raised to x, 0.5 raised to x divided by x factorial. So when we put in this equation 0, it is e raised to minus 0.5, and that's how then e 0.5 raised to 0 by 0 factorial, which is equal to this e raised to minus 0.5. We get its value using calculator or some tables, and its value is 0.6065. So what is actually 0.6065? It's the simplified value of e raised to minus 0.5. Likewise, we can determine all these probabilities by putting the values 1, 2, 3, 4, etc. When it reaches at 6, the probability becomes very negligible. That's why we are not recording its value, and we can see in the graph at 0 the highest probability nearly 0.6065, at 1 it is 0.3032, at 2 it is 0.0756, and these squares represents the probabilities at these points, or the heights represent the probabilities at these points, and this in the values 4, 5, 6, etc. They lie on the value x-axis, the values axis itself, because their probabilities are very negligible. Anyway, we note that the shape is positively skewed. Now, next we take a situation of Poisson distribution with parameter lambda equal to 1.0. Here also we have a positively skewed shape. At initial values of this random variable, we have higher probabilities, and thereafter the probabilities are getting reduced when we come to the higher values of this random variable x, that is at 0.36787, at 1 also same probability, 2, 3, 4, etc. The probabilities are getting reduced. Now next is 1.75, again the shape is positively skewed, and next is the value 2.75, again the shape is positively skewed. Our point is, when lambda becomes larger and larger, the shape becomes symmetric. That's our point. So we increase the value of lambda successively. So here lambda equal to 4, that is why x follows p of 4, and here the shape is better than the former shape. It is close coming to almost a symmetric shape, that is 5. Now next is 6. No, so not 6, 7.5. Now I increase that lambda to 12. So we have more symmetric shape when lambda becomes 12, and when lambda becomes 25. Okay, it comes to almost a symmetric shape. When lambda becomes 50, more symmetric shape, and when lambda equals 100, we get a very symmetric shape. That means it's an indication of this. Lambda tends to infinity. Lambda becomes larger and larger. The shape becomes symmetric. So we have very good evidence of this symmetric approach of this graph to symmetric shape when lambda becomes infinity. So thus we conclude that the frequency curve is always, for most cases, positively skewed, but when lambda becomes larger and larger, it attains the shape of symmetric curve. Thank you.